Alright. Hey, welcome to our meeting on recurrent neural networks and LSTMs. Before we get started, I just have a couple announcements about the rest of this week and next week. This week, we will be having no speaker event like we did last week. Our next speaker event will be next Thursday. It will be Professor Razvan Marinescu, who will be coming in over Zoom, and he will be talking about his research in the healthcare space and how he's using artificial intelligence within his own startup, his research, and just in general here at UCSC. So make sure to come in for that. It's going to be super fun. It will be a great learning experience for all of you guys. I can definitely say it will be for myself as well. Secondly, there is no meeting next Tuesday on the 14th. So no meeting next Tuesday, but we will have a speaker event on Thursday. So keep that in mind. We will be making an announcement on all of our channels. So on Discord, on Instagram as well. So no meeting Tuesday, speaker event next Thursday. Professor Marinescu from 6 to 7 on Zoom. We'll be posting the Zoom link then. But those are just a few announcements before we get started today. So without further ado, let's get this show rolling. So this is our next topic in this quarter. As if you guys have not noticed the theme by this point, we are talking about neural networks all throughout this quarter and the different models and how they can be used. So this week, we're going to be talking about recurrent neural networks and then adding on to that long short-term memory or LSTMs. So let's get started. And I'm clicking, I always click the wrong one. Or does this work? Let's get it. All right. Okay, cool. So before we talk about RNNs, let's talk about feed-forward neural networks or FFNN. So what I did was I put this picture up here, and I wanted you guys to kind of discuss, but you guys are all sitting like 3 to like rows apart from each other. So what I want you guys to do is just think individually, based on this image here, and the input layer, the hidden layer, the output layer, the directions of the arrows, what can you kind of infer, and what can you infer about what this neural network does? So I'll give you guys like a minute for you guys to think about it, and then I'll call you. So maybe 30 seconds. And if you guys have something, raise your hand. Or just blurt it out. Any takers? Sure. Yeah, that is a commonality in not just feed-forward neural networks, but in a lot of neural networks. That's a great observation. Anyone else? All right. Cool. So here are the biggest 3 kind of inferences that hopefully you might have seen, but you weren't sure, or you just didn't know, and that's perfectly fine. So number 1, information is only flowing in one direction. You get inputs from your input layer, and you're getting it from the output, and you're getting an output from the output layer, right? It goes in from point A, comes out from point B. As simple as that. We go from an input layer to a hidden layer, and then to our output layer, right? Some values come in and some values come out. And the biggest thing is there are no cycles or loops at all in this network, right? You have no arrows coming back into your hidden layer and then going back out, right? You guys can all see that? Cool. So this comes into the next kind of evolution of the feed-forward neural network into a recurrent neural network, all right? So right off the bat, got this GIF over here. I'll let this play out, but automatically you can notice the difference between a recurrent neural network and the feed-forward neural network already. Number 1, you can handle sequential data, all right? So I can say the best way for me to put it is as it goes through this kind of time, it can look at previous inputs and it can use those to make predictions about the current step, right? So RNNs are used heavily in natural language processing as well because of this very feature, because it has the ability to memorize. You can get context, you can understand the weights between words, and you can make more effective predictions based on that. And if you notice the structure, you have your input layer down here, your hidden layer in the middle, and your output layer up here. So the architecture of a recurrent neural network is kind of rotated such that you have your input layers, at least the way I remember it, you'll start with your input layers on the bottom and you work your way. So, all right, so some key features you can have, and really, I think this picture does a lot of justice. So when you think about recurrent neural networks, this picture is really good for remembering. So, and the biggest thing is that you have the same weights for each and every one of these computations, right? You don't have to really adjust too much, all right? Yeah, that's all I wanted to say on this one. Cool, all right. There are types of RNNs. You have many-to-one, one-to-many, and many-to-many. All of these are fairly self-explanatory. Many-to-one, you have many inputs to one output. One-to-many, you can have one input into many outputs. And then many-to-many, you can have many inputs into many outputs, right? And some examples of where these could be used. You can use them: A, sentiment classification; B, image captioning from one to many; or many to many has multiple applications. All of these have multiple applications. I encourage you guys to look this up too on your own, and so you guys get a better understanding and a visualization rather than just graphs. Cool. All right, so what is the math, the real math behind this? All right, so it essentially works as your kind of hypothesis or your current hidden state, right? Your current hidden state is equal to the weight and the previous hidden state, and current input vector. It's missing a bias term in there as well.
That's, to clarify, that's the function. To do
yeah, the function.
Combined in any number of ways, but the function is always the same.
Right. So usually it will have a bias term associated with this, but that is just associated with the function. So the function is usually equal to the weight times your parameters plus a bias term. And what I want you guys to do is to think about what a problem could be with this. And I'll give you guys a couple of minutes, or like a minute, and then I'll take answers. And if you guys have an answer, if you have something that you think, then shout it out or raise your hand. Need takers. Nope. Cool. All right. Yep. Bam. So there are two main problems with recurrent neural networks. The first being the exploding gradient problem. All right. So here, as said, is this working now? This is not working. All right. I think it just died. Or I turned it off. Nice. All right. And so now these work. All right, cool. So is the exploding gradient problem. In very simple terms, it is very self-explanatory as well, right? Your weights compound on each other and they get way too big very, very quickly, right? You could start in this extreme case, 2 to the 1 is 2, and then you get into your next step is 1024, and your next step is just insanely large, right? That doesn't help your model learn anything, and you actually lose information through time, right? With each step, you lose information, and your output does not accurately represent your input and what you should be receiving as output, right? So how do we fix this? You have generally two options. A, you could use gradient clipping. If it gets too large, you can always rescale it. And secondly, you can use like a sigmoid function or some activation function to keep the weights constant. All right. Cool. Yeah, that is also true. No, I got it. All right. Secondly, the second problem is the vanishing gradient problem, right? This is just the inverse of the exploding gradient problem. With the exploding gradient problem, you have your weights compounding on each other massively. Here's the opposite. Here, your slope, if you were to graph this on some graph, it diminishes rapidly with time to the point that it's almost zero. That does not help our model at all. And through time, through our network, you lose information with time, and you just don't get the correct output. So depending on what your model is trying to do, your output should be able to accurately predict based on your input. The vanishing gradient, if you have this kind of a problem, your slope is going to decrease at an exponential rate, and you are going to, just like the exploding gradient problem, sorry, you are going to lose information through time. How do you solve this, right? Just like with the exploding gradient problem, we had solutions here, gradient clipping and using bounded activation functions. Here, we can do something very similar. We can reinitialize the weights through each pass, or B, you can use or select the right activation functions, just like with the vanishing gradient, just like with the exploding gradient problem, albeit you'd have to invert it. And lastly, the biggest kind of step up from a recurrent neural network is long short-term memory, all right? And that is the second half of what we're going to be covering today. RNNs are the foundation for what LSTMs are built on. LSTMs, when you think of natural language processing, you obviously think of using a recurrent neural network first, but LSTMs have much more, I would say, prowess in remembering context and something called long-term dependencies, right? So I want to go through a couple of examples. I want you guys to, as we get into discussing long short-term memory, or LSTMs, which is what I'll call them from here on out, as we get into discussing LSTMs, I want you guys to think about long-term dependencies. What are long-term dependencies, right? I want you guys to think about it. What does this kind of phrase mean? When you think of natural language processing, when you think of predicting what you guys will be doing actually later today in the project, is predicting the kind of last word in a sentence or a phrase based on some given input. What does the phrase long-term dependencies mean to you guys in that context? I'll give you guys a minute, and then if you guys have an answer or anything, blurt it out. If not, raise your hand. I'll call in. Any takers? Sounds good. All right, no problem. All right. Long-term dependencies in this context means context. When you're given a sentence, let's just say, I want you guys to fill in the blank for these next couple slides. The clouds are in the what? Anyone? Sky. Cool. All right. Why is it sky? Why did you pick sky? But like, within the context of the sentence, that is a fair answer. Your mind immediately goes to sky. But when you look at it in the context of the sentence, why would sky be the first, or not the first, but for you, why would it be the first thing that comes to mind? Right. Yeah, exactly. We, by looking at the structure of the sentence, the first thing that we look at is like this noun, clouds, and we have this phrase here, are in the. So that's specifying like a location where are clouds usually found, the sky, right? For this example, is there any external context? Is there a long-term dependency here that we need to know for why the clouds are in the sky? Is there any external information, or is it just like we know the clouds are in the sky, so our fill in the blank is going to be sky? The answer is no. There are no long-term dependencies here. For just one sentence, you could use a basic recurrent neural network to figure out the fill in the blank here, that the clouds are in the sky, right? Let's look at a more complicated example. All right, tacos are my favorite. Blank food is the best. What goes in the blank? Exactly, right? So tacos are my favorite. Mexican food is the best. Why Mexican? Right, exactly. So did you need to remember, or what context did you need to figure out the blank space there? Mm-hmm. Yeah, exactly. So what we needed to do for this example, tacos are my favorite. Blank food is the best. Well, I can't say French because if I was just going off individual sentences, I could say French, I could say like American, but that's not true here. We have a dependency. We have a long-term dependency, and that's tacos. Tacos we know is Mexican food. Therefore, when I come into predicting this blank space here, I know that the subject of my previous sentence was tacos. Therefore, this blank should be Mexican, right? You guys with me on that? So let's go to the next example, right? Now, the same thing will apply here, right? I lived in France for 10 years. I can speak fluent. Yeah, you guys can just say it. You guys don't have to. French, right? I lived in France for 10 years. I can speak fluent French. This is the same thing that applies. What's up? Someone say anything? No? All right, I thought I heard something. All right. I lived in France for 10 years. I can speak fluent French, right? It's the same thing that we talked about here. We know that we need context to answer this last fill in the blank, right? This, if my model outputted like Spanish, would it make any sense within this current context? No, right? We need to understand the subject for the previous sentence, get this dependency. We need to remember that we're using France, right? So that when I come into my output, I can speak fluent what? I know my dependency from my last sentence, or my context for my last sentence is France. Therefore, my answer should be French. You guys see how we're doing that? For us, it's basic intuition, right? We don't need to really think much. Like you said, right? Your brain immediately goes, the clouds are in the what? Sky. I know the clouds are in the sky, right? Your computer does not know that. RNN will not be able to do that, right? At this level. So what we kind of just went through was we went through the process of how an LSTM works at a very high level, right? We remember the context, and depending on the context that we may have, let's adjust our current output so that it matches the context, right? So let's get in the weeds a little bit into long, short-term memory. So themes, right? Before we get into it, right? We didn't need any context, any further context for clouds, right? The clouds are in the what? They're in the sky, right? Secondly, for our second and third examples, tacos gave us the context to Mexican, and France gave us context to French, right? In these examples, right, if you notice, these dependencies are immediate, right? It's sentence to sentence. I can say I lived in France for 10 years. I can speak fluent French, right? That's my next sentence. But what if I can speak fluent French already, and then I had completely unrelated sentences, and then I brought it right back to talking about this subject, right? You can use an LSTM to still remember this context so that maybe 100 lines later, you can adjust for this context in this sentence, bring it back down to wherever you're referencing it, and then I'd say French or something, or baguette, or whatever it is, right?
Break down one sentence is like tracking one word from you.
So what you're doing, so just for our examples here, this is mainly looking at the subject of the sentence, right? And adjusting for like the noun or for like the adjective, right? So if you, just for our examples, but it can be anything. In the project that you guys are going to do, it can vary, right? But the main idea is staying the same. What we need to understand is context to a sentence or to a phrase, so that when we predict our current output, or when we predict our output, it should match up with the context of the previous sentence, or the previous, or what that phrase was implying. So it doesn't always have to be a subject. I could be predicting a verb. I could be predicting an adjective, an adverb, a pronoun, a noun, and within the context of NLP, I could be predicting anything, right? But as long as, like, if I was trying to predict a word, if I said like, someone was running a marathon, blank, so Bob blank, 2 miles, right? You'd use ran or something like that, right? That is a verb. It's not a noun, right? So it doesn't always have to be the subject. I know I'm rambling a lot, but it doesn't always have to be the subject. It can be any place in the sentence. Can I answer your question? Awesome. Okay, let me go back down here. All right, so it is possible. The biggest thing that I wanted to say about this last point is that you can have gaps between dependencies, but your LSTM will still remember. All right. So let's get into the weeds a little bit and let's see exactly how this happens, right? Using long short-term memory, or LSTMs, right? Fill in the blank. What? All right. Let's use this example. All right. We're going to predict this blank space using an LSTM, and we're going to go through a step-by-step process in figuring out how we can predict this blank spot here. All right, using an LSTM, and we'll go over the architecture and all of these different steps as well. All right, Jesse is such a good salesman that he continues to get returning customers as well as new ones. Blank was awarded Employee of the Month. What should go in the blank spot? Jesse. All right, we know this. We know what our output should be. Let's walk through our LSTM and let's see how we can get that current output. All right. Cool. All right. So this is a very basic structure of an LSTM. That looks very scary. Trust me, it is not. All right. We're going to break this picture up into 3 steps. All right. So our LSTM works in 3 steps. Each one of these scary looking figures is not very scary at all. It's actually the biggest, each function is very important in its own way in predicting our output and remembering context, right? And keeping context in mind, all right? So LSTMs work in a 3-step process. Step 1, if I have 2 sentences or 3 sentences, and one of them makes no sense to what we need to find out, then I don't need it, right? Let's not remember information that I don't need. So we're going to forget all irrelevant aspects of our previous state, right? Secondly, we want to selectively update like our cell values with what we are currently remembering from the previous state. and what we're trying to predict. And then lastly, our prediction in our last output gate. All right, so let's walk this through. Let's walk it through. All right, step one. All right, what do we need? What do we need and what do we need to forget? All right, so how do we do it, right? I wish I could say it's magic, but there is no magic, right? You can use the forget gate. Very simply, our step one is called the forgetting step, right? So let's walk it through. We have let's say our previous step was, we had a couple of sentences, or the sentence, Walter is good in chemistry, Jesse on the other hand is good in carpentry. And we have our X input, Jesse is a great salesman. Yesterday he mentioned he always gets repeat customers, right? For our sentence, for our fill in the blank, do we need this first sentence, Walter is good at chemistry? No, right? We just need to forget it, right? How do we do that? We can use the forget gate and this f of t function, which we're using a sigmoid function of the weight vector of the weight vectors times the function plus this bias vector, not vector, plus the bias, right? I don't want you guys to worry too much about the math behind it, but it's always good to know what is going on. So we don't need this Walter is good in chemistry. That's not what we want. We want everything related with Jesse, right? What do we forget? We forget this Walter is good in chemistry. All right, next step. All right, now that we have that, right, how much should this unit add to the current state? That's like our second step, updating the current cell, right? Not bad. All right, there are two parts to this step, but it's very simple. We have our input gate, and then we multiply by this tan h, our tan h function here. So what do these do, right? Our sigmoid layer, what parts of our current state make it to the output? And then our tan h, we apply a weightage on it. So what words do we actually need to remember? What holds more importance over the other? So if we look at our sentence here, if we look at this example here, right? Jesse is a great salesman. Yesterday you mentioned whatever, right? What do I need to remember? I need to remember Jesse. I need to remember salesman. I need to remember like repeat customers or something like that. Like, do I need to remember that very often? No, right? So so we're going to apply weights to each one of these, to each one of our words here, and especially the ones that we need to remember. All right. Then we're going to multiply it with the tan h. So that's what we get over here. And lastly, new information can be added. So if you have another sentence to this gate, and you can pass it through the sigmoid function, and you can update it and then multiply it, and then you'll have adjusted weights. All right. So the math part, I won't get too in the weeds for, but if you would like to, we are going to be posting the slides later. You can come back at it and look at the math portion so you guys get a better understanding. So at a very high level, that's what the math is doing. All right. So any questions on step 1 and 2, by the way? Nothing? All right. If you guys have any, please ask. Here to answer. Oh, wrong way. All right, cool. Now our last step, right? This is where we actually predict, right? So what part of the cell state should make it to the current output? All right, number one, we just need to run a quick multiplication between our sigmoid function and our tan h function. So we're going to run a sigmoid layer, which decides what part of the cell state makes it to the output, just like we did over here. So all the sigmoid functions are doing is very similar through each step. And then lastly, we're going to multiply it to our tan h value, and we're going to set that value between -1 and 1. Now, if you notice the direction of the arrows, you can remember the fact that you predicted this and send it back through your network, or you can just send it directly as output, right? So given this, and this is our output gate. So if I go back through it, you have our forget gate. What do I need to forget? Our input gate, what do I need to update? And lastly, our output gate, And then this, you can, using whatever value you get here, you can send it back through the LSTM, or you could use it as your output. All right. All right, so given that, given those, so let's see what exactly happened, right? We understood that Walter, we didn't need it. We remembered everything with Jesse. And so now when you give it the sentence, Jesse is such a good salesman, we know, all right, we can identify Jesse, we can say good salesman. All right, we've applied those high weights to it. So we're automatically trending towards this. He continues to get returning customers as well as new ones. Blank was awarded as employee of the month. You can't say Walter here based because we already forgot, right? We can only say Jesse for this current context. Does that make sense? So
How would you know when to send it back?
that depends on the architecture of how you are trying to on how on your implementation. Yeah. So any other questions? Cool. All right, let's code. I forgot to put the link up. It needs to be tiny URL. All right. Want to start exporting it? Want to start exporting it? Or
Oh, actually, good one.